Okay, guys, this is going to be the video answer key for practice 4.3. Now, I've done this before a couple of times on our practice pages, where I'm going to go back to the notes that we took yesterday so I can copy the two equations that I need. So we know there's two equations that are really important here. So you should get out your notes from yesterday, and that is our projectile calculations notes. And what I'm going to do is I'm going to copy the two equations that I said were really important. Okay, so first off, I'm going to copy out this equation right here. So this is my big horizontal equation. And so I'm going to copy that, and I'm going to put it right at the top of my page. And so this is something that you guys can do. Okay, you can put the equations at the top of your page that you know you're going to need to use. I'm going to go and I'm going to take that one, and then I'm also going to take this one. Okay, those are my two really important equations that we learned yesterday. So I'm going to put them right at the top of the page. And what you should do is just go ahead and, whoop, just go ahead and write those at the top. I'm going to make them a little bit bigger. There we go. Okay, so now I've got my two equations written at the top. Now let's start in on number one. So Tom Cat is chasing Jerry Mouse across a table that's 1.5 meters high. Jerry steps out of the way at the last second, and Tom runs off the edge of the table with a horizontal velocity of 8 meters per second. Okay, so part A just asks us to draw a diagram. And so I'm not talking about a motion diagram. I just want to picture the situation. And so I'm going to make mine actually look like a table. You don't even have to be that complicated, okay? Really all we need to see is the trajectory. So if I had a table, okay, not very fancy, and I know that the cat is going to run off the edge and he's going to fall and hit the ground, okay? So now all I want to do is I want to go and I want to label the stuff that I know, all right? So for instance, I know that the height of the table, okay, so the height of the table, which we're going to call yi, is 1.5. And you can look up on the board and see that yi is equal to height. I also know that the initial velocity, okay, is 8 meters per second. So the speed that he was running at the beginning is 8 meters per second. There's still some other things here I don't know, all right? So like, for instance, I don't know delta x, okay? So that's a question. And then I also don't know delta t. That's a question, and that's time. Obviously, we can't draw time on the diagram. So that's about what my diagram can look like. I'm just labeling the parts. I'm trying to get a visualization for the problem. Okay, how much time does it take before Tom hits the ground? Well, now I know you guys have a hard time starting, okay? You're having a hard time just figuring out what process to use. So use this process, guys. First, write down what they gave you. So they gave me yi, and they gave me v. Okay, that just comes right out of the problem. That just comes right from there and there. Now write down what they want me to find. So how much time does it take? Well, that sounds an awful lot like delta t. So delta t is my question mark. This right here is a great way to start. Write down what you know. Write down what you're trying to find. Now you can pick an equation to use. So in this case, the equation that I want to use, if I look up here, well, and I'm going to highlight some stuff. You guys don't need to highlight right now, okay? But what I want to see is I'm trying to find delta t. Well, delta t is actually in both of my equations. So delta t itself doesn't tell me which one to use, okay? So I have to look a little bit deeper. So I have to look and see, all right, if I'm going to find delta t, that means I need to know every other variable in the equation. So if I'm going to use this equation, that means that I have to know v and I have to know delta x. Otherwise, I can't solve for delta t. Now, the issue here is that I know v, that's 8, but I don't know delta x. That's a question mark. So if I don't know delta x, then there's no way I can use that equation, which means I probably have to use this equation. But let's look at it just to make sure, okay? Zoom in, there we go. Okay, so if I'm going to solve for delta t, that means I have to know every other variable. And the only other variable is yi. And I know yi. I know that yi is 1.5. So that means I can use this equation. So that's the one I'm going to use. So I'm going to go down here, and I'm going to write in yi equals 4.9 times delta t squared. It doesn't really matter if the square goes inside or outside the parentheses, guys. Now I'm going to plug in. I know that yi is 1.5. So 1.5 equals 4.9 times delta t squared. Now, one of the big mistakes I saw people make is they were subtracting 4.9. Don't subtract 4.9. You got to divide by 4.9. Okay, and I'm going to do here. Actually, you guys can. I'm going to do this on my calculator, guys. I'm not going to show it to you just because it's going to go faster if I do it on my calculator here on my phone. So 1.5 divided by 4.9. It's 0.31-ish, okay? Now, I'm just leaving. It's actually 0.306122245. I'm leaving all that on my calculator, okay? 4.9s cancel out. And I've got delta t squared. Now I need to get rid of that squared, so remember the next step is to do the square root of both sides. That's going to cancel out the square root and the squared and leave me with just delta t, okay? And then the square root of 0.306 blah, blah, blah is actually 0.55, and that is seconds. All right, so there's that one. Next, how far does Tom land from the edge of the table? Okay, so from the edge of the table, Tom is going to, so how far does he land from the edge of the table? So if I look up here, really what I'm looking for now is I'm looking for delta x, okay? That's what I want to know. So, again, so now I know delta t is 0.55. I know that v is 8. I know that yi is 1.5. And I'm looking for delta x. Now, this is pretty simple, guys. Delta x is only in one equation, okay? This equation here, I don't know why it won't zoom. The yi equation doesn't have a delta x, so I can't use it. So I have to use my delta x equation. All right, so I'm going to go delta x equals v times delta t. And then I'm just going to plug in, okay? So v is 8, delta t is 0.55, so delta x equals 8 times 0.55, and so delta x is going to equal, now, if you just multiply 8 times 0.55, you're actually going to get a different number. I still have 0.553283334 on my calculator, so I'm just going to multiply that times 8, and I'm going to get 4.43, and that's meters. Okay. Now, draw a horizontal motion diagram for Tom's motion. All right, so motion diagrams, remember that's dots and arrows. Now, Tom's running on the table, okay, and he's running at a constant speed. He's running at 8 meters per second, okay? Then he runs off the edge of the table. And remember that horizontal motion has constant velocity. Okay, so my dots aren't going to get any closer or farther apart. They're just going to stay the same distance apart, and my arrows are going to stay the same length, okay? And so we'll say that, we'll say that's 0. All right, cool. And I'm just going to put this note in here. This is constant velocity. All right. Now, it wants the vertical, so it wants the up and down motion diagram. Okay? So, we're going to do this. All right? So, we'll draw our down arrow. Now, at the beginning, Tom is not moving up and down. So, when he is running, okay, when he's running on the table, before he falls, he's not going up and he's not going down. Okay? So, really, what we want to do here, you don't have to draw all that, sorry if you did. He's not moving up and down. He's staying in the same spot. So just like we used to stack dots on top of each other, to show something staying in the same spot, we're going to stack dots beside each other to show them staying in the same spot. And then he starts to fall, okay? And his dots are going to get farther and farther apart. And the reason for that is that he's speeding up. So the big key here, side to side, constant velocity. Up and down, speeding up. All right, number 2. Imagine that you're trying to flick a piece of popcorn off the edge of your desk so that it lands in a bowl on the floor. The desk is 1.25 meters tall, and the bowl is 0.5 meters from the edge of the desk. So I'm going to draw a picture. So again, I'm going to draw a desk, okay? I'm going to draw a little piece of popcorn. There's going to be a bowl down here, okay? And I want the popcorn to go in the bowl. Now, there's a couple things they told me, okay? So they said that the desk is 1.25 meters tall. So I know that yi equals 1.25. All right? It also said that the bowl is 0.5 meters, so we did 1.25. It said the bowl is 0.5 meters from the edge of the desk. So I know this. Zoom. I know that distance, delta x, is 0.5, okay? Now, I don't know the velocity, and I don't know the delta t, but I do know those other two things. All right, so how long will a piece of popcorn be in the air? So remember, guys, let's just start with what we know. We know yi. We know delta x. I'll do 0.5. And we're trying to find how long will it be in the air. Well, that sounds like a time, so that's delta t. Okay, so when we go look at our equations, same thing we thought about for the very first question on here, okay? So I'm looking for delta t, but it's in both equations. They gave me delta x, but they didn't give me v. So I can't use that equation. So that's out. But they did give me yi, so I can use that equation. That's in. All right, so let's use that equation. yi equals 4.9 times delta t squared. Okay, now I know yi. It's 1.25. So I'm going to go 1.25 equals 4.9 times delta t squared. Okay, now I'm trying to solve for delta t. So just same process I did before. Divided by 4.9. I'm going to do that on my calculator here. So 1.25 divided by 4.9. So it's like 0.25510. I'm going to call it 0.26, but I'm leaving it on my calculator. Okay, then I'm going to square root both sides, and I'm going to end up with delta t equals the square root of 0.26, which is 0.51. 0.51 seconds. Cool. Okay, what horizontal velocity do you need to flick the popcorn with? So now it's looking for velocity. So I know yi is 1.25. I know delta x is 0.5. Now I know that delta t is 0.51, and I'm looking for velocity. Well, if I'm looking for velocity, then it has to be this equation because it's the only one with velocity in it. Okay, so delta x equals v times delta t. And I'm going to plug in delta x, and I'm going to plug in delta t. So I've got 0.5 equals v times 0.51. I'm going to divide both sides by 0.51, and I'm going to get v equals, and 0.5 divided by 0.51. Let's see. Sorry, I got to go to my calculator. Clear. 0.5 divided by 0.51 equals 0.98. 0.98 meters per second. And that's my velocity. Cool. Okay. If you got somewhere around 1, that's fine. Now, horizontal and vertical velocity versus time. So this is velocity versus time. So remember, side-to-side velocity. Side-to-side velocity is constant. Side-to-side velocity is constant. Get that tattooed on your face. Side-to-side velocity is constant. So to show constant velocity, which in this case is 0.98, okay, I'm going to do something like, I'm going to say 1, 2, 3, 4, and I know that my velocity is just below 1. So that velocity is staying the same, okay? It's staying the same the whole time, just right around 1. Okay, now vertical velocity, all right? So up and down velocity, well, we know it starts at 0, okay? So there's 0. We know it starts there, okay? And it's going to decrease just like that. And so, well, it's going downhill, but it's actually getting faster, okay? So anytime it's falling down, that's what our vertical velocity versus time looks like. All right, guys, nice job.